Okay, a very, very good day to everyone. Now we are going to take up few concepts on the decay rate, right? On the the decay rate and in general half life. So this is not exactly a very, very specific topic for today. It's more or less few expressions and one or two problems that we'll take up on radioactivity. So if you have over here a sample which is radioactive over here and it has a decay constant of lambda, then number of active nuclei after a certain amount of time is given as the initial number of active nuclei e power minus lambda multiplied by t, the time which has elapsed, right? Now the half life over here is related to the decay constant as t half is nothing but natural log of 2 divided by lambda itself, right? And what about the decay rate? The decay rate is also known as the activity. The symbol is capital A. It is the initial activity e power minus lambda into t itself. The number of the decay rate or the number of disintegrations which occur per second or per unit time, right? We'll simply call it as a decay rate. So as the time passes, the decay rate also will decrease. Initially you have a very high decay rate, right? Initially large number of molecules will be undergoing decay over here per unit time, right? So let's take over here a question. What we can say is that let's say that there is a sample A and B, both are radioactive. This one has a half-life of let's say Ta. This one has a half-life of let's say Tb, right? We'll write Ta half and Tb half just to be clear. And let's say that initially the decay rate of A is n times B, right? Initially the decay rate of A is n times that of B, let's say, right? Then you're asked to find out at what time will the decay rate of A and B be the same. At what time the decay rate of A be equal to that of B. So we'll just start with that itself. We'll simply equate the decay rates itself. Why not? So over here you can write that the decay rate of A, let's say A1, is equal to the decay rate of B, which is nothing but the initial decay rate of A into e power minus lambda 1 into t becomes equal to the initial decay rate of B into e power minus lambda 2 into t. Now what is said about the initial decay rate? That data we have. Fortunately we do have that. The decay rate of A is n times that of B. So let's substitute that over here. Initial decay rate of A is n times the initial decay rate of B e power minus lambda 1t. This side it is a naught b e power minus lambda 2t. That's all, our job is done. You cancel these two and shifting the n over here on one side, you can always write e power minus lambda 1 plus lambda 2t. On this side you have 1 divided by n. Let us take the natural log over here on both the sides. You get natural log of 1 by n, and over here you'll be getting the lambda 2 minus lambda 1 multiplied by t, natural log of e, which is 1 itself, and our job is done. So we can write over here, this is t, this is lambda 2 minus of lambda 1. This is equal to natural log of 1 by n, or you can write natural log of n as equal to lambda 1 minus lambda 2 times of t itself. That's it. So the time taken is natural log of n divided by lambda 1 minus lambda 2 In terms of t half you want to write, just go back over here to this relation. If t half is natural log 2 by lambda, what is lambda? Natural log 2 divided by t half. That's all. Let's substitute that over here. This is natural log of n divided by natural log of 2 divided by t half of a minus again natural log of 2 divided by t half of b. Ln 2 you can take a side over here and you can simplify this particular result. This is our final answer. This part is clear, gentlemen. No doubts are there. Yes. Excellent. Excellent.